Alright, buckle up everyone. Because while OpenAI's new O3 model has set the AI world on fire by smashing various benchmarks, the bigger story is that it's both astonishingly powerful and still surprisingly fallible. Let's take a deep dive into what makes this model so revolutionary, yet intriguingly imperfect, and explore the fascinating details that many discussions might miss. First off, let's talk about those jaw-dropping performance metrics. O3 isn't just incrementally better than its predecessors, it's rewriting the record books. In software engineering and competitive coding challenges, O3 outperforms the previous best model, O1, by more than 20%. We're talking about a system that can outcode 99.8% of human programmers, which is simply staggering. In competitive mathematics, O3 achieves a 96.7% accuracy rate. And when it comes to PhD-level science questions, the improvement over previous models is so dramatic, it's almost hard to believe. But the most significant breakthrough comes from O3's performance on the RC-AGI benchmark, widely considered the gold standard for measuring an AI's ability to handle novel, unseen problems. On the semi-private evaluation dataset, O3 scored 75.7% in low compute mode and reached an astounding 87.5% in high compute mode. To put this in perspective, humans typically score around 85%, and previous top AI models, including the entire O1 family, couldn't get past 32%. This jump from 30% to nearly 90% represents one of the most significant leaps in AI performance we've ever seen. However, here's where the story gets really interesting and humbling. The ARC-AGI testing team has revealed specific examples where O3 completely fails, even in its high-powered mode. Let's look at some of these fascinating cases in detail. In one example, they presented a grid with blue indicators at the borders, where connecting these indicators would turn all red boxes along those rays blue. It's a pattern that most humans, even children, can quickly grasp through simple visual reasoning. But O3 stumbles, even when the test input only slightly increases complexity with a second line. In another revealing example, O3 was given a sequence of color-coded bars, blue, red, green, and light blue, and had to apply learned patterns to additional objects. While it could handle the first two cases, it failed when asked to extend the pattern to a third object. These aren't complex theoretical problems or advanced mathematical concepts. They're the kind of puzzles that rely on basic pattern recognition and logical extension, something human brains do almost effortlessly. The technical architecture behind O3 is equally fascinating. According to Francois Chollet, who helped create the RC benchmark, O3 employs what he calls natural language program search and execution within the token space. During inference time, when it's actually trying to solve a problem, O3 searches through possible chains of thoughts or programs that might solve the task, similar to AlphaZero's Monte Carlo tree search. This process is guided by an internal evaluator AI model, which helps it navigate through potential solutions. The computational demands are staggering and worth examining in detail. In low compute mode, O3 processes around 33 million tokens per task. But in high compute mode, that number skyrockets to nearly 6 billion tokens. This translates to about 13 minutes of processing time for a single answer, with the system utilizing thousands of GPUs to explore what Chollet describes as an enormous number of possible paths through this huge program space. The system effectively performs a deep search through all possible solution paths, including extensive backtracking when it hits. The cost structure of O3 reveals just how computationally intensive this new approach is. The low compute version, which achieves that 75.7% score, runs about $20 per task, already significantly more expensive than traditional API calls. But the high compute version that hits 87.5%, we're looking at around $1,800 per single task. This explains why early rumors of a $2,000 monthly subscription model were quickly dismissed as unrealistic. You'd burn through that amount on just one or two high compute queries. These costs aren't arbitrary. They reflect the massive computational resources required for O3's unique approach to problem solving. What makes O3's architecture particularly groundbreaking is how it approaches novel problems. Unlike traditional AI models that rely heavily on pre-training and fine-tuning, O3 performs what researchers call test time adaptation. When faced with a truly new task, it essentially needs to relearn or deeply search for a solution on the spot. This process involves exploring an enormous space of possible solutions, guided by its pre-trained knowledge but not limited by it. It's like having a brilliant student who, instead of just recalling memorized answers, actively works through each new problem from first principles, just at an incredibly accelerated pace. The semi-private evaluation dataset that revealed these capabilities consists of 100 specific tasks, carefully designed to assess AI models' generalization capabilities on novel, unseen problems. It's deliberately withheld from the public to prevent training data contamination, serving as an intermediary between public datasets and completely private evaluation sets. According to Cholet's technical report from December 2024, these tasks specifically target an AI's ability to handle problems it's never encountered before, making it a crucial test of true intelligence rather than mere pattern matching. Comparing O3 to its predecessors in the O1 family reveals the magnitude of this advancement. While O1 models, low, medium, and high versions, topped out at around 32% on the semi-private evaluation dataset, O3 more than doubled this performance even in its low compute mode. The jump to 87.5% in high compute mode represents nearly a 3 times improvement over the best previous results. Interestingly, OpenAI skipped the O2 designation due to potential confusion with a British mobile service provider, making O3 technically only the second iteration in this series. The way O3 processes information during inference is particularly fascinating. During that 13-minute processing window, the model isn't just thinking, it's actively exploring what Cholet describes as a forest of thoughts, or more complex tree structures. This exploration involves generating multiple possible solution paths, evaluating them, backtracking when necessary, and continuously refining its approach. It's almost like watching a grandmaster chess player consider countless possible moves, except O3 is doing this with abstract reasoning patterns at an unprecedented scale. Looking ahead, Cholet and his team are already working on ARC-AGI-2, scheduled for 2025, which promises to be even more challenging. They're specifically designing it to probe O3's limitations and push the boundaries of what's possible in artificial general intelligence. The current version of O3, while groundbreaking, still shows fundamental limitations in its ability to ground its understanding in reality, relying heavily on token space evaluation rather than true conceptual understanding. For those excited about using this technology, OpenAI plans to release O3 Mini in late January, followed by the full O3 model. However, given the computational requirements we've discussed, it's likely that the full model's capabilities will need to be significantly scaled back for practical use. The mini version will presumably trade some of that 87.5% performance for more reasonable operating costs, though exact specifications haven't been released yet. The implications for the field of AI are profound. O3's approach suggests that we might need to fundamentally rethink how we evaluate and deploy AI systems. The traditional metrics of parameter count and training data size might be less relevant than a model's ability to perform effective search and reasoning during inference time. This could lead to a new paradigm in AI development, where the focus shifts from bigger models to smarter inference strategies. The question of whether O3 represents true AGI remains contentious. While its performance on certain benchmarks is superhuman, its failures on seemingly simple pattern recognition tasks reveal that we're still missing crucial components of human-like intelligence. The fact that it requires such extensive computation and search processes to solve novel problems, something humans do effortlessly, indicates that we're dealing with a fundamentally different kind of intelligence. Moreover, O3's dependence on massive computational resources raises important questions about the scalability and practical applications of this approach. While it's impressive that we can achieve human-level performance on certain tasks, the energy consumption and financial costs make it impractical for widespread deployment. This suggests that future developments might need to focus not just on raw performance, but on finding more efficient ways to achieve similar results. As we look toward 2025 and beyond, O3 stands as both a spectacular breakthrough and a humbling reminder of AI's current limitations. It's pushing the boundaries of what's possible, while simultaneously revealing new challenges we hadn't even considered. The race to develop more efficient, more capable AI systems continues, with each advancement bringing both exciting possibilities and new questions about the nature of intelligence itself. What's clear is that we're entering a new era in AI development, where the lines between training and inference are blurring, and where the ability to reason about novel situations is becoming as important as pattern recognition. Whether O3 represents a step toward true AGI or simply a more sophisticated form of narrow AI remains to be seen, but it's undeniably changing how we think about artificial intelligence and its potential.